then. So yeah, whenever you're ready.
All right, thank you. Thanks, I'll come back. Thanks for coming in again. So to continue, so what we started yesterday, namely, so yesterday we discussed sequences of ideals which were similar, and more precisely, I called these an ink invariant or sim invariant chain, where these ideals were in polynomial rings in, well, I denoted these by kxn for short, but more precisely, I probably should have written, I could have written C times n. C is fixed, the number of rows of variables, and then we have in each row n variables. This is what this means. So the number of variables in the polynomial rings grows with n. And we had seen by requiring some invariance, we get stabilization of generators. No, sorry. And to recall what was meant is if we have a sim invariant sequence, then there is some index n0, and if we take the generators of the ideal I n sub 0 and apply sufficiently many, all the permutations on n letters to these generators, we get a generating set for the nth ideal in the sequence. And similarly for ink, there's another, the same thing, but instead of applying permutations, we apply increasing maps. And sorry for being unclear, increasing for me always means strictly increasing. I want an injective map all the time. And so there is this set of stabilization, which is in a sense, and the generating set, you can think of it of one invariant of an ideal. And today the theme is, well, what can we say about other invariants? So is there also a way to predict these invariants, at least for large enough indices n and ideals I n in the sequence? We will make one assumption throughout. We will assume all the ideals are homogeneous. And that's pretty harmless. So, which means they are generated by homogeneous, or they have each idea has a generating set consisting of homogeneous polynomials, and to be where we assume that each variable xij has degree 1. So standard grading of a polynomial ring. And again, if we have finitely many variables, Hilbert gave us a blueprint how to do this. And so let me recall this. It came already up in Martina's lecture, but let me state it the way we want to use it. So we take an idea J in a finite polynomial ring in finitely many variables. Let's call these y1 up to yn. Let's call this polynomial ring S. And this, maybe I emphasize it once, if this is a homogeneous idea, then we consider a formal power series. As follows, and we denote this by h sub j of t. T is a new variable. And we take the sum over j at least 0. And then, because we made the assumption that j is homogeneous, we can S mod j becomes graded, meaning we could take the residue classes of homogeneous polynomials in S of degree j form a vector space. It has a finite dimension. And so we'll take this dimension, multiply by t to the j. And then Hilbert showed this is actually a rational function, and it has a very particular form. Namely, you can write this as a polynomial h of t over 1 minus t to the power d, where h of t is a polynomial with integer coefficients, and h of 1 is not 0. So in particular, that the fact that h of 1 is not 0 makes sure that this fraction is in reduced form. So maybe we should write this so we have a certainly a reduced form. And so that makes this expression, this rational function, unique to describe this formal power series. And in Martina's lecture, we have seen if we do this, if J is the Stanley-Reason ideal of a simplicial complex, then this numerator polynomial is determined by the phase vector of the simplicial complex. So that indicates already this is, the numerator is interesting, and the denominator is also interesting. But before I say this, what has this to do with the theme of predicting invariance? The fact that this Hilbert series, well, this formal power series is called Hilbert series. So let me rewrite the name again. The Hilbert series is rational of this form, could be expressed differently as follows, or equivalently. So far, that these dimensions of these vector spaces of degree j polynomials in S mod j, or this is given by a polynomial in J if J is sufficiently large. In other words, well, if it's given by a polynomial function, once you can predict the values, right? Once you, if you know this is a polynomial and you know sufficiently many initial terms, well, you can interpolate and you can predict what all the other dimensions have to be if J is large enough. So this is the blueprint, but before we come to this, there's more information. I mentioned already that we had seen the numerator determines the of a, in case of a Stanley Reason ideal of a simplicial complex is determined by the phase vector. We had also seen the denominator is actually determined because this number d is, well, the dimension, or more precisely, the Kroll dimension of S mod I. And when the number h of 1, which we know is not 0, this is actually called, or either the multiplicity of S mod j, or if you think geometrically, it's typically more denoted as the degree of j, and that is h of 1, and that is actually positive. That's a positive integer. And so this is called the degree. And maybe to recall, if S mod j is the Stanley Reason ring of a simplicial complex, then this number d determines the dimension of the simplicial complex. It's d minus, the dimension of the simplicial complex is d minus 1. So for Stanley Reason ideals, you have already seen that these the information given in this Hilbert series is actually useful and interesting, and one can define these invariants in greater generality, and they are always, I mean, actually it turns out they are always of interest. So we are motivated to simulate this in the case we discussed yesterday. Now, yesterday we passed first to infinitely many variables. And so we could wonder, well, what about an analog if we consider an ideal, well, in infinitely many variables, say in 0 variables. So just to recall, that just meant the variables xij, I varies between 1 and c, and j is a positive integer. But that does not work. Because, well, if you want to form the quotient of the polynomial ring by the ideal, if this ring has infinitely many variables, there is no way to be sure, and in fact it would be often not true, that this vector space dimension is finite. And then the very definition of a formal power series is already a problem. So we cannot do this, and instead we will consider a chain of ideals as discussed yesterday. So we take a chain of ideals I with elements in, or as mentioned above, in these polynomial rings with finitely many variables. But I should pause to ask for questions first before I make the next definition. Any? All right. So then, we use this, when we want to use this idea, we have a sequence of ideas. Now, each ideal lives in a polynomial ring with finitely many variables. So then we can form the quotient ring, look for polynomials of a fixed degree. That will always be a finite dimensional vector space. So it makes sense to put forward the following definition. And for this chain, we want to also define a Hilbert series, and we call this the equivariant Hilbert series. Of this sequence I. And now it's again a formal power series. But now we use two variables. S and T. And we define it by, well, we denote by, first of all, H of I. And then, well, for each ideal in the sequence, we have a Hilbert series. And then we sum over these various Hilbert series. So we take sum n at least 0, and then we sum over these Hilbert series polynomial ring modulo the nth ideal. That's a formal power series in T, and then we multiply by the new variable s to the nth power. So if we write this out, this is the sum n is at least 0, j is at least 0, and when we sum over the dimensions of sum over vector space dimensions of polynomial ring with c times n variables modulo I to the n in degree j times t to the j times s to the n. And there's one piece that I still have to define, namely, when I said here n is an n, we start natural numbers. I start with 1, but here I start a sum with 0. So we make a definition. We define this quotient to be k if n is 0. Okay. So, and of course, well, one can make this definition. And the question is, well, is it something nice or could it be any useful? So that's, well, maybe before proceeding, any question about the definition itself? Now then, let's do a toy example. Namely, let's consider the 0 chain. Let me denote this by O. So this is the sequence O. And what I mean by the 0 chain, well, all ideals are just a 0 ideal. So then in the definition, well, we just have the Hilbert series of the polynomial rings, and that is easily determined. So we want to compute with equivariant Hilbert series of the chain. So we have to sum over the Hilbert functions, Hilbert series of the polynomial rings k sub n in variable t times s to the n. Now this is a polynomial ring kxn. I dropped the c as usual. So this is a polynomial ring in c variables, c times n variables. And so its Hilbert series is 1 over 1 minus t to the c power cn times s to the n. And then, well, I leave this out to you to one step to confirm that this is 1 minus t to the power c over 1 minus t to the power c minus s. Okay, so, and if you have never computed the Hilbert series of a polynomial ring, well, I gave away the answer. I encourage you to follow up with this as an exercise and also to fill in the dots here.
Did you forget a sum in the?
Oh, yes, I did forget the sum. This you could not verify. But if I add the sum, thank you, Aida, then this makes a lot more sense. Okay. Then, well, the good news is this is, again, a rational function, and it doesn't look so bad. Well, it shouldn't be, because it's an easy example. But actually, that this is rational is not an accident. So this happens all the time, at least in the situations we discussed yesterday. And so this is a result, well, it's a rather recent result together with Tim Römer, namely, if the chain of ideals we start is inc invariant or sim invariant, then, then we can always write this equivariant Hilbert series to the sequence as, well, it is a rational function, and we can say something about the shape of this rational function, more precisely about the denominator. So first of all, the numerator is a polynomial in 2 variables, and denominator is, so what we can say about the denominator is what are the possible irreducible factors of the denominator. And they have a restricted form, so we have 1 minus t to the power a, and then we have a finite product of other factors, and each of these has the form 1 minus t to some power minus s times a polynomial in t. And so what are all these numbers? Well, as one would hope, a, b, and c sub j, these are integers. Oh, I should have said this first, sorry. And they are non-negative integers. Moreover, these numbers c sub j are at most c again the number of rows. The numerator g of s of t is actually a polynomial with integer coefficients. And then we have polynomials fj of t. They also have integer coefficients, and they satisfy well, fj of 1 is positive. Moreover, more recently, I could show there's another condition we have to satisfy. If we evaluate these polynomials at 0, well, you don't get 0, but 1. So this actually happened just last year. Before saying more, I should point out, well, actually, let me make a remark. Or maybe again, first questions about the statement. Again, I mean, it's a rational function. All the polynomials that show up have integer coefficients. And as you can check, these factors are irreducible polynomials in S and T. So that gives a description of the, some description of the denominator. Now, let me make 2 remarks. First, the rationality of this equivariant Hilbert series has been also shown independently by, in a paper by Krohn, Lakin, and Snowden, which appeared in the same year. But I mean, yeah, 2017 has been the date of appearance, but they proved it after the result with Tim Römer. And I will come back to this result, or actually their method of proof, and then I will abbreviate this by KLS. The second remark is for those who know enough algebra, for Hilbert's result about Hilbert series, that is actually true not just for homogeneous ideals, it's actually true for arbitrary graded modules over a polynomial ring, and there is also a version of the result I mentioned for graded modules. And that's actually, I mean, this is in the paper where we showed this improvement, but I won't discuss this. This requires much more algebra and other techniques. So but there is more in case you're interested. All right. Okay. So let's look at some examples. So first, we considered yesterday the sequence of ideals where the nth ideal was generated by the 2 minus of a generic matrix. And so let's consider this example again. So in is 0 if n is 1, and otherwise it's generated by the 2 minus of the matrix, well, with C rows and n columns, and then position ij, one has the variable xij. And in this case, the classical Hilbert series is known. So the Hilbert series of the nth ideal, n at least 2, is when, well, 1 over 1 minus t to the power c plus n minus 1. And the numerator polynomial is the following. We have a sum j from 0 to c minus 1. And the coefficient of t to the j is c minus 1 choose j times n minus 1 choose j. And that's the coefficient of t to the j. Yeah, so as I said, this is the of course the numerator. But if you believe this, then I encourage you to compute as an exercise what is then the equivariant Hilbert function, where we will sum over these expressions for as n varies, and then you will get 1 minus t minus s to the power c plus s times 1 minus t to the power c minus 1 over 1 minus t minus s to the power c. And so, and in a sense, this looks even simpler than the individual Hilbert series here, so that's actually nice. Now, as another example, let's consider any homogeneous ideal. J and infinitely many variables, say y1 up to yc. And we had seen yesterday, one can use any ideal in infinitely many variables to generate an invariant chain. And so we want to do this, and let's do this in a particularly simple way, namely consider the following. So we denote the first ideal in the chain. That should be an ideal in k x1. And we have c rows, so the indices of the variables are x11 up to xc1. And we denote by this just the ideal obtained from J by simply substituting for yj. We just take the j's variable in the sequence, so we choose xj, comma 1. And then we denote by I, consisting of ideals in, be the inc invariant chain. generated by I. Sorry. Or by I1. So what does it mean? We let In be the ideal obtained from I1 by applying all strictly increasing maps that map 1 to an integer which is most n. And in this case, we can compute the equivariant Hilbert series, assuming we know the Hilbert series of J, the standard Hilbert series, namely, if the Hilbert series of J, classical Hilbert series, is h of t over 1 minus t to the d, if h of 1 is not 0, then the equivariant Hilbert series of the chain generated by I1 as described is 1 minus t to the d's power over 1 minus t to the d's power minus s times h of t. Okay, and now let's recall what Hilbert showed. If h of 1 is not 0, it's actually positive. And moreover, it's easy to check that h of 0 is always 1. Now, for lack of space, I ask you, just remember this part, these conditions, and then let's go back to the theorem. This is a factor as we described, and we have these two conditions. So that's exactly what h gives us. So that shows whatever numerator polynomial is possible classically in a Hilbert series may show up as this polynomial here. All right. Any questions?
So is it like, I don't understand why we don't get some C in this last expression? I mean, the things we've seen so far were including always like 1 minus t to some exponent including C.
Well, I mean, so the power Cj is just, well, in this case, what is Cj in this case? That is our D.
Mm-hmm.
And what I said is, I mean, in this case, the D is one of these Cj's, and it's at most C. And that is actually true because D would be the core dimension of this polynomial ring modulo J. But the polynomial ring has the dimension C. So the quotient has certainly a dimension which is at most C.
Yeah. Okay.
Does this work?
Yeah, makes sense. Thanks.
Okay. Other questions?
Does the numerator have any kind of like combinatorial interpretation in terms of the simplicial complexes if you have a square-free monomial ideal?
Great question. I bet it does, and I ask you to find out.
Okay.
So yeah, so I was, okay, so I will describe one more example. And typically, and this will be basically all the examples I'm aware of. So there is a lot to be explored and that should be computed. And I bet there is some interpretation as there is in the classical case, but it hasn't been found yet. And one reason is, I mean, there's certainly a lack of examples, and that's why we also proposed as one of the open problems to really just try to compute these things in a number of interesting cases. Because, so let me describe one more case just to illustrate what I just said, where we know, and then I can also say what we already don't know. So let's, maybe I do this. So this is together with a I should write this better, sorry. Günther-Kühn. And well, it appeared in 2018. So let's do this in a case where we have only one row of variables. And then let's consider the chain ink invariant chain generated by one monomial. And I need to write it down to have some notation. So let's say the indices of the variables are mu1 up to mu_r, and the exponents are a1 up to ar. And we order these variables so that mu1 is less than mu2 up to mu_r. And so I meant this chain. So what this means is, maybe just to recall, I could have write this succinctly or short. Yeah, succinctly, we take the orbit of this monomial and cut it back to the polynomial ring in n variables. And then the equivariant Hilbert series is of the following form. It's 1 minus t to the power mu sub r minus 1. So mu sub r is the highest index of a variable appearing in M. And then we have a product I from 1 to r. And we multiply 1 minus s times. And then the polynomial in t is just the sum of powers of t from the zeroth power to the power ai minus 1. And the numerator, I mean, this is also determined. Let me not, it would take a while to state it. So let me just say it's also determined. And analogously, you can do this if C is greater than 1. But what is already open is if we replace ink by sim. So if you apply not just increasing maps, but all permutations, depending on the monomial we stored, if the exponents a1 up to a are all distinct, we get many more generators. And there should be also a formula. Well, we know there is a formula It should be just determined by the information encoded in the polynomial, but it hasn't been worked out yet. It hasn't been computed yet. And watching the time, I realize it's time for a break. So, well, before, until we discuss questions possibly. Okay. Yeah, I hinted at this already. So I described basically 3 examples where I know what this equivariant Hilbert series is, and that's pretty much it. So lots more examples are worth being worked out. And I actually will give a blueprint how to do this a little later. But before I do this, I want to provide some motivation for actually carrying this out. Namely, coming back to the original motivation, we wanted to predict some invariance. So is this rationality actually good for something? And it turns out the rationality alone doesn't do the job, but we have the information about the denominator. And that is the key to show that we actually can predict some invariance. And this has been also shown in the paper with Tim Römer. Namely, if IN, they form an, if this is invariant chain, or analogously sim invariant, then the sequence of dimensions of these quotient rings of the nth ring modulo the ideal of n is given by a linear function. And it's a linear function in n. If n is sufficiently big. And so we had seen if you start with a square-free monomial ideal that corresponds to a simplicity complex, you can form a sequence of simplicity complexes, and the dimension of these complexes will grow linearly eventually. You can also say something about the degree of I to the n, not I to the n, the nth ideal in the chain. And now this is growing much more rapidly because that is given by an exponential function in n. And more precisely, or eventually, one could say could form where R integers kappa greater than 0 and lambda at least 0, such that if you take the degree of I to the n, divide by kappa to the n times n to the power lambda, and let n approach infinity, this limit does exist, and it's actually a positive rational number. So these are the two statements combined. The limit does exist, and it's a positive rational number. And in particular, we can modify, we can form two limits which will always be integers. So we can, the linearity result, of course, about for the dimension implies if we take the limit as n approaches infinity of the dimension of the rings, the nth ring divided by n, that will be a non-negative integer. And similarly, if we take the nth root of the degree of I to the n, this limit will exist as n approaches to infinity, and again, it will be a non-negative integer. Okay, so during the break, I was asked, what do these numbers mean? Well, great question, and I don't really have an answer. I mean, initially I would think, well, one could think sort of, this is, I would call this the dimension of the sequence, the chain. And this is at least asymptotically the sort of the degree, but what it means precisely remains to be seen. So let me, however, there are cases where it's known what it is, namely, so this limit, you can, this has been determined explicitly if you know the generators of the ideal, or at least the ideal that generates the chain. This has been known if each in is a monomial idea. And that is in work with Le Nguyen and again Römer. The second limit is more mysterious. So let me recall this result. I mean, the work with Semmer Günther Kuhn, where we discussed these ideals, which are the chain, which are determined, this is determined by one monomial. Then this limit, well, it should be determined by the information in the monomial. And we did this. However, I admit I didn't expect the answer. I mean, I had expected somehow like the sum of the exponents, right? The degree of the monomial. But instead, it's the maximum of the individual exponents. And, well, okay. So, as mentioned, these are basically the examples I know. On the other hand, one could compute lots of more examples in principle. And this is what I want to talk about now next, how to do this. And so for this, we will shift gears and we'll talk about finite automata and regular languages. Okay, so and we'll start with the languages. So let's, from now on, sigma be a finite set. And sigma star be the set of finite strings of elements in sigma. So this is actually the same. We used this star notation already yesterday. And if you want more algebraically declined, you could call it sigma star the free monoid generated by S. And now, so first of all, what's a formal language? L in the alphabet. Sigma, so we refer to sigma as the alphabet, is just any subset of sigma star. So in other words, well, other words, we will refer to these finite strings as words in the language, L. Now, what is a formal language? And this definition is somewhat implicit. So let me define what is the class of formal regular languages. Sorry. Okay. Regular languages on the alphabet sigma. And this is the smallest class of languages satisfying the following two conditions. First, maybe I say it even before I write it, it should contain all the languages which consist just of a single letter in the alphabet or the empty word. So containing all languages having a single letter element, it's the same as an element of sigma or the empty word as their only word. And then this class of languages should be closed, undertaking unions concatenations and I should say finite unions, finite concatenations, and passing from a language N to the set N star. And if it's true, then, for example, this class, one can show this will be also closed undertaking intersections. So it's really just the class of the regular languages are really just described by the descriptions, right? You have, so what the first part says, well, I mean, every language consisting just of a letter as the only word is in there, but then you can take finite unions. So that means every finite subset of sigma star will be a regular language, but then there are many more. And so let me look at some easy examples. Let's assume our alphabet has only 2 letters. And then, well, what is, if I take the language consisting just of A and then pass to the set of sequences of letters in the set of sequences of letters or words in the language, I just get A to the N. So A to the N is just the word A repeated N times. And that is then certainly regular. S is the language where I start with the language I just had, but then I could also, instead of starting with A, I could start with B, and then form the concatenation. Just appending every word from the first language by a word in the second language. And what I get is words of the type a number of A's repeated and then a number of B's. And that's it. And these are regular languages. However, even when you have only 2 letters in your alphabet, there are non-regular languages. So if your words are of the form, you have the first letter N times, and then the second letter also N times, the same number of times. And N is at least 0. This is not regular. And well, so intuitively, you could think of it, what are these abstract descriptions? I mean, if you have a finite set, well, that's easy. And then you can take unions, concatenations, and passing from a set to strings of elements in the set. So this allows you sort of a formulaic description of your language, where you don't have to remember what came before. And in this case, you wanted to determine if a word is in the language, these have to be equal, and that just doesn't work. You cannot do this. And get a so consider this as an exercise. But now, why do we care about this? And so we only use it. So how do we use this? The idea is what we want to do now, we want to encode monomials in our polynomial ring. So we want to encode monomials in our polynomial ring with C row variables by words in the alphabet sigma, and we have C rows of variables, and then we have C plus 1 letters in the alphabet, tau, theta 1 up to zeta C. So how do we do the encoding? We define a map mu from sigma star into the monomials in our polynomial ring. By the following 3 rules. Sorry, that was not intentional. So first, the empty word gets mapped to 1, to the identity. If you have a word theta I followed by W, that gets mapped to the monomial, the monomial xi1 times mu of W, and if you have a tau followed by W, that gets mapped to, well, apply capital T to the encoding of W. And now I have to say, what is capital T? This is the shift operator, which, well, it takes every column index and increases it by 1. So in other words, tau applied to xij is x sub I j plus 1. And then you extend this multiplicatively. So in words, what does it say? So what are we doing? We replace every theta I by xi1 and every tau by by t applied to the string following it. So let me do this next. Well, as there are immediate questions, maybe let's do an example. So let's look at the word tau, tau, theta 1, tau, theta 2, and then maybe again tau. All right, so what did we say? So we applied tau, replace tau by t, and this is twice. So you have to apply twice t to whatever follows. But this is a theta 1, so we replace this by x 1, 1. Then there's a tau, replace it by t. And now we have to, well, what follows is a zeta 2. So that becomes x2, 1. And then there's another t, a tau, which becomes a t. And that's the end of it. So we interpret this as the empty word. So we have to apply it to t of 1. And now we compute this. So what was t of 1 is 1. And so what we get is, well, in the first step, we get t squared of x1, 1. And then we apply t to x2, 1. So we shift the column index, we get x2, 2. And now we have to shift the column index twice. So we get x1, 3 times x2, 4. All right. Questions? Okay. So let me, I know there are lots of words here, but in a sense, this procedure is pretty straightforward. I mean, well, as I stated, you replace the theta i's by the corresponding variables, taus by these shift operators, and then shift column indices according to the number of taus and where their position is in the word. Okay, so and now I encourage you to actually to think about this gives you, this map mu is certainly surjective and you can make it injective. And this is actually what Krohn, Lakin, and Snowden did. I mentioned them before. They showed for any ink invariant chain IN and at least one, there is a regular language L such that the encoding we just discussed, mu, induces a bijection from a sublanguage of L, I will denote by Ln, and say what it is, to the monomials in In, where Ln in L is the set of words in which the letter tau appears exactly n times. All right, so in the idea of proof is pretty well, pretty natural. First of all, since regular languages are closed undertaking unions, it's enough to discuss this for the chain generated by one monomial. And if you have one monomial, he can work out what this language L is explicitly. And if you fiddle around with this recipe, how we encode, it's actually not too hard to do this. All right. Well, have you gained anything? Right? So what did we do? Right? We have an infinite set of
Sorry, Uwe, can I ask something?
sure.
When you say the monomials of In, do you mean like the ones that appear in the support? Okay.
Yes, thank you, Alessio.
Okay.
I realized sequence of monomial ideas.
I also have a question.
Yes.
So it's kind of bugging me in the example that the tau, like the last tau didn't do anything. And it's worrying me that like, wouldn't this make it hard to have a bijection if like some of the letters aren't?
Great question. Well, I want this because I want to count the number of letters tau appearing, because they correspond to the ideal monomials in In. And now, so if you take, for example, the monomial x1 squared, well, this could appear in the first ideal in the sequence, but it also could appear it will appear in the second ideal, in the third ideal, but you have to count all these monomials differently. So if you want a bijection, you have to keep track of the same monomial appearing in several ideals. And this is what the letter, recording this letter tau here serves. It doesn't change your monomial, but it keeps track where you are in the sequence.
Okay, that makes a lot of sense. Thanks.
Actually, this is a great question. Thanks for asking it. All right.
I have another question if I can.
Yeah, sure, go for it.
So yeah, another thing that confuses me about this bijection is the fact that, for instance, mu of Z1, Z2 should be the same of mu of Z2, Z1. Is that right? So
absolutely correct. That's why, that's a good point. That's why I said it's, well, in the first step, it's not so difficult to show that this bijection, this encoding is actually surjective. If you want a bijection, you have to make your domain smaller. So what you can do, you insist, for example, you insist in your words that if you have consecutive zeta letters, zeta 1 comes always, all the instances of zeta 1 come before zeta 2, followed by zeta 3, and so on. If you have a tau, then you start over again, but you can't have zeta 2, zeta 1. For the very fact you just mentioned, because the polynomial ring is commutative, but our set zeta star is not. So you're forced to make this call, but you can do this and it will still be allow you to get a regular image.
So we are not allowing to reverse the order in our language ln.
Yeah, I mean, no, exactly. Yes, you cannot allow this if you want a bijection.
I see.
Yes, and you can just insist when you just, I mean, at least in words, I just did, right? You consist only these words where you specify the order. If you have a substring consisting just of zeta letters, you insist that the indices, the zetas with smaller index become before anyone with, come first before any other index. And you can still guarantee that this gives you a regular language. Maybe it's also a good exercise to to think about why this is still a regular language.
Thanks.
Mm-hmm. Okay. Then let's do one more example, or actually related. So and you could think of, actually, maybe I encourage you to think of this as an exercise. And I avoid the problem where Alessio just I think it was Alessio pointed out, I just say C is 1, so I have only one zeta letter. And then let me write, for simplicity, tau, no, just zeta instead of zeta 1. And then, as I mentioned, it's enough to do to understand the proposition for just a chain generated by a monomial. So let's do x1 squared. And where we start with I1, that is the ideal x1 squared. And so x1 squared appears for the first time in the first ideal. So that means you need one tau and there's a square. So therefore the letters zeta has to show up at least 2 times. And pretty much these are the only conditions. So you can write for the language zeta tau, and then you take all sequences of zetas and taus, followed by zeta zeta. Again, any sequence consisting of zetas and taus, but then you absolutely need to go make sure you have one tau, so you put this to the right. That will do the trick in this case. All right, so okay, so that we have a few more steps to do this. So what have we achieved? If you have a chain of invariant chain of monomial ideals, if you want to compute the equivariant Hilbert series, we have to count monomials in these individual ideals. This bijection shows equivalently we could count words in these languages Ln. And well, to do the counting, we'll define also a formal power series. And because it will turn out, because of this bijection, this power series will be exactly the equivariant Hilbert series we are interested in. So in the next step, we will, instead of counting monomials in In, we count words in Ln and form a power series. That sounds, again, like shifting the difficulty from one instance to another instance. But when the point is in the final step, it's known that you can actually describe all regular languages using what's called a finite automaton. And then I will describe tomorrow, once you have a finite automaton, you can write an explicit formula for what is your formal power series. And that formal power series will determine, is the same as the equivariant Hilbert series we are interested in. And that works for every sequence of monomial ideals. And as we discussed in the break, if you start with an arbitrary ink-invariant sequence, using the black box Gröbner basis, which I don't want to go into it, you can pass to a sequence of monomial ideals with the same equivariant Hilbert series. That's also algorithmic. And then you could run this algorithm if I have started describing now, and we will continue tomorrow. And then you in principle, it's a finite algorithm. And so one could follow the steps and compute examples. And in my opinion, this absolutely should be done much more systematically than it has been so far. But let's save this for tomorrow. Questions?